Hey class, Adam Ward here. I want to work through an example today about using forces on planar surfaces. The idea here is we're going to let those hydrostatic forces we've been talking about start to interact with the rest of the world. Goal here is to see my thought process, how we set up, think through, and solve a problem of this sort. So the exercise we'll work on is hydrostatic force pressing on a gate, shown in red in the diagram on the right-hand side. The idea here is we've got a gate hinged at the top. It's 4 feet in and out of the page or the screen. We have a hinge that the gate could rotate around, and we want to keep this gate closed so the water stays in the tank. So the question is, how much force do we have to apply down at the bottom edge of the gate? In other words, what's the magnitude of that holding force P required to keep this from moving? Okay, let's get into it. So the first thing that we're going to do is start with a free body diagram for our gate. So we're going to isolate that gate to analyze and document all the different forces that are acting on it and that from which it is acting on the world around it. Of course, in orange at the hinge we have those reactionary forces, and I'm showing them with an X and a Y component just to keep my life organized, since those are the primary dimensions we'll use in the problem. That's the force that arrives anytime we've got a hinge where something could rotate around it. We also potentially have reactionary forces to keep it in place. That's the reason the pin exists on the hinges on your doorway. Shown in red is the resultant force. That's the fluid pushing on the gate. Fluid always acts perpendicular to the surface it's pushing on, so we've drawn it as such. In blue is that force P to hold the gate in place. And it's potential that we would think about the force of gravity acting on the gate itself. It may be a big heavy steel gate. Now, I'll grant you that in this problem we don't get any information about it, so we're going to assume it away, but nonetheless, for completeness, we're going to show it here. So with this in mind, then we need to think about a strategy for solving this problem. And in general, there's 3 equations that we could manifest. We can sum the forces in the x direction, we could sum the forces in the y direction, and we could sum the moments around any point in the problem, although the hinge is typically where we'll pick for reasons that will become evident in just a moment. So should we sum the forces in the x or the y direction? We absolutely can, but when we do so, either one of those equations is going to have some component of P, which is unknown, and it's going to have a reactionary force, Hx or Hy. And so one equation with 2 unknowns isn't enough. We absolutely could manifest those 2 equations, but that's going to be 2 equations with 3 unknowns, Hx, Hy, and P. So we're going to ultimately have to manifest the sum of the moments around the hinge. And we're doing so in large part because the moment arm is 0 for Hx and Hy. Because they go through the hinge, they don't create any rotation. It's not that those forces don't exist, it's that they don't create a net rotation. Your door doesn't spontaneously rotate around the hinges if no other forces act on it. So by doing so, we can drop those 2 out and end up with one equation with one unknown, P. And as I mentioned, we're going to, from this point forward, assume that gravity is negligible because we don't have enough information to deal with it. So that green Fg will disappear. All right, team. So with that, this is the spot where you should hit pause and try to formulate that moment equation before I do so. Okay. Here's my solution to the problem. I'm going to sum moments around the hinge, and I'm going to set that equal to 0. You can see over on the right in bright green, I've drawn around the hinge kind of that little rotational circle with a plus. I've decided counterclockwise will be positive in this problem. If you do it the other direction, the math will still work out. It's important we're consistent. So when I think about the forces I need here in my moment balance, I've got the force P. That's acting 6 feet away from the hinge, so my moment arm is 6 feet. And directionally, it's got a negative sign in front of it because it would cause a clockwise rotation, negative in my convention. The second piece here will be the resultant force, Fr, acting at some distance away from the hinge. Now, the resultant force itself is something we've been working on in class, so that hopefully you've got a strategy to calculate. And I want to look at the moment arm for just a moment just a moment for the moment arm. In orange, I've drawn the distance YR. That's the thing that we can typically calculate. It's the along the plane distance from the water surface to where the resultant force acts. In this case, because the water surface is not coincident with the hinge, YR isn't the moment arm. We only need that little section of distance between the hinge and where the resultant force acts. Now, from the geometry of the problem, that means I need to know YR, labeled in orange, and then I need to subtract off 10 feet because that's not part of the moment arm. So let's work through this together. Resultant force, specific weight of the fluid, times vertical depth to the centroid times cross-sectional area. You can see on the right-hand side I've labeled that vertical dimension HC. So that's measured vertically up and down to the centroid of the gate itself. And to find that, we can abstract from the problem this right triangle geometry, where the vertical leg is HC, the hypotenuse is 13 feet, that's the diagonal distance down to the centroid, and we've got that angle of 60 degrees given in the problem. So HC can be calculated as 13 feet times the sine of 60 degrees. Pro tip here, make sure your calculator is in degrees, not radians, to get this problem correct. And then the area of the gate itself, 6 feet along the diagonal, and then 4 feet in and out of the page. So when we go through and complete that calculation, I get about 16,900 pounds. So we've got the magnitude of FR. The last thing we need is YR, that distance. And so we know that YR can be calculated as Y to the centroid plus that second moment of inertia, IXC, divided by YCA. So in this problem, YC is 13 feet. That's the hypotenuse of that green triangle that we drew in the bottom right. I filled that in 2 locations. Area, just like above, 6 feet by 4 feet. So the thing you should be asking yourself right now is, hey Adam, where'd that 0.23 feet to the fourth come from? That's that second moment of inertia. And I looked up the equation for this. For a rectangle, it's 1/12 times the length of the base times the length of the other dimension of that triangle to the third power. So 1/12 times 4 feet times 6 feet cubed. Again, that's from a lookup table in chapter 2 of our textbook. That equals 0.23 feet to the fourth power. When we combine this all together, we get a YR of 13.23 feet. And I'm just noticing here as I record this problem live for y'all, I'm not sure that this 13 is actually correct because I took this 0.23 and I forgot to divide it by these things down below it. So something in here is not mathematically correct, but I'm noticing it as I'm recording this thing live. We're going to roll with it and see what happens. So thank you for your patience with me as we go through this. Well, let's see what else happens. We pull down that information from the top, we plug in the values that we've just come up with, and we can calculate a resultant force P, or excuse me, a holding force P of 9,100 pounds. And what I want to acknowledge to y'all right now is I think that my answer is numerically correct. And I think that 0.23 is, let me grab a different pen color here. This chunk that I'm boxing in, I think that totals up to 0.23 feet, and that this IXC value in the numerator is actually different. I'm sorry for having that typo in the slides, but at least we caught it in real time, and hopefully that's making sense for y'all to fix it. Alright folks, hopefully this helped you see how force balances and moment balances can let our resultant force from the fluid start to interact with the world around us and contribute to a design in an engineering application. That's what I've got. Hope this finds you well, and I'll see you back in the classroom. Thanks everybody.